Okay, and so for this last slide, let's compare these two methods, doing a cofactor expansion across a row versus going down a column. And let's just make sure either way we do it, we get the same result. I'm not going to prove this theorem in general, but at least we can verify it works for this example. So let's take this matrix, this 3 by 3 matrix A that we've been working with. Column 1 is 3, 1, 2. Column 2 is -1, 2, 0. And column 3 is 2, 0, 1. And we can compute the determinant of this matrix going across a cofactor expansion across a row as we've been doing. So when we first calculated this determinant, we chose to go across the very first row. So we fixed I equals 1, and that's what I've got shown in red in this formula. And then we kind of filled in all of the values for what A11, A12, and A13 were, as well as the submatrix for A11, A12, and A13. Then we calculated the determinants of each of these 2 by 2 matrices and simplified, and we found that the determinant of this 3 by 3 matrix A was -1. So let's compare that calculation to what it would look like if instead we were to do a cofactor expansion down a column. In this case, let's pick a column that has a 0 in it, since that will cut down on the calculations a little bit. And that's why I chose column 2 over here. And so doing the cofactor expansion down column 2, we would start by taking A12, which is this entry right here, the -1, and then we're going to multiply by the determinant of submatrix A12. Then we're going to go to the next entry in the column, which is down to the 2 over here, A22. And then we cross out the entries in the same row and column as it, and then we're left with a 2 by 2 submatrix. Recall that we call this A22. And then we go to the last entry in this column, which happens to be 0. That was the nice reason for picking this. And so we eliminate all of the entries that sit in row 3 and column 2. And what's left over is going to be submatrix A32. And these are the components that we're going to need to calculate the determinant of A. And so down below, I'll show how that work goes. So I would take my first A12 entry, and that's -1. And because 1 plus 2 is 3 is odd, we have a negative in front of it. So I've got minus because this is odd. I've got a -1 because that's what entry A12 is. And then I'm multiplying by the determinant of submatrix A12, which is the 2 by 2 matrix. The first column is 1, 2, and the second column is 0, 1. Then we add, because now we're at entry 2, 2, which is even. So we add to that A22, which is equal to 2, times the determinant of submatrix capital A22, which is this 2 by 2 matrix. The first column is 3, 2, second column is 2, 1. And now we chose column 2 because the third entry in this column, A32, I'm going to subtract it because 3 plus 2 is 5 is odd, but A32 is 0. So it really doesn't even matter what submatrix A32 is or what its determinant is. Whatever it is, we're going to multiply it by 0. So it's going to not contribute anything to the determinant. And what's left over is the determinant of this first submatrix A12 was 1 minus 0, so it is a 1. So I have this minus sign that I grouped in with the -1, so that becomes positive. This determinant is +1. Now I've got the +2 times this determinant is 3 minus 4 is -1, and then we have a 0 from that last term. So altogether we have a 1, a minus a 2. This gives us -1. So we can see coming down column 2 gave us the same determinant as if we came across the first row or came across the second row or came across the third row. So we can be strategic and save ourselves some effort by choosing an appropriate row or column to do the cofactor expansion.